Okay, for those who feel that last week's presentation wasn't quite cheap enough, we have the now even cheaper Live Math Edition. So I'm just going to do this live. Literally, I hope. I'm alive. Anyway, on the channel that I keep forgetting the name of for bizarre reasons, which is called Mind Your Decisions, done by Presh Talwalker. This week we had a problem which I virtually guarantee I'm not going to solve for you here and now. First, addressing the question of why on earth am I doing this? I really think, as I think I said last time, but I'm going to say it again anyway, that too often we see math professors, math teachers presenting a proof or working out a problem, but they already know the answer. They already looked in the book. They already have the solution in their mind, and they're just basically taking it from their notes, transferring it to whatever kind of medium these days, some kind of LCD projector probably. And they already know what they're going to do before they start. I think that sets up the wrong kind of expectation in the mind of a lot of students, particularly at the undergraduate level, where you start to think, well, if I look at a problem for more than 30 seconds and the answer just doesn't flash into my brain, I must not be cut out for mathematics. I must not be any good at this. I should probably just give up. That isn't, in my experience, the way real working mathematicians really work. I have made a living off of mathematics and computer programming for many years. I consider myself essentially a professional mathematician. I'm not an academic, but I'm the programmer they call in when they need someone who understands a lot more math than the average programmer does. And programmers are usually pretty good at math. I'm better. Anyway, enough egotism. Today we're going to see how I don't solve this problem. Feeling that I'm pretty confident in my abilities, I've looked at a lot of the Mind Your Decisions problems, which are very good. You should definitely go over to Presh Talwalker's Mind Your Decision site. You should like, subscribe, and share everything that he does, especially these days. If you look back at some of his earlier videos, they help to inspire me because they look almost as bad as my videos. But the new ones are really good. You should be sharing and liking the heck out of those, and you should be working on those problems. I'm going to show you what it looks like when I start trying to work on the problem he posted, I believe, sometime yesterday. We are given, as I understand it, and it's even possible that I'm misunderstanding this problem, I'm going to give myself a limit here on how long I'm going to work on it. Partly because I may have misunderstood the statement of the problem. Even misunderstanding a problem, you can learn things. One of the things you hopefully learn is you keep throwing things at the problem, hoping that something will stick. That's how 90% of doing a proof works. Most of the students I've ever known who are good at proofs are the ones who are persistent. The ones who don't just give up after I tried 1-2 things and they didn't seem to be working, so I gave up on it. They're the ones that throw out crazy ideas and say, well, what if we draw a line way over here? Or what if we were to squash this thing flat? Or some bizarre thing. They keep trying crazy things until they either go crazy or they solve the problem. So the problem, as well as I understood it, was we are given a circle. We are given a diameter of that circle. We have the points A and B that touch the circle on that diameter, and we're given a third point, C, somewhere on the circle. And we want to create a perpendicular from C to this line, the diameter. With the minor problem that we don't have a compass, we just have a straight edge. This is part of the area where I'm not quite sure about the statement of the problem, but I'm assuming by straight edge, the intent is to mean what it usually means, that we can create a line anywhere where we've got 2 points, but we can't measure anything. If we could, it's not a ruler. A ruler and a straight edge are 2 different things in geometry. So, one of the few things that I can see to do right off, and this is the point where, yes, I have looked at this problem for about 15 minutes. I haven't solved it, and I'm only giving myself about 5 more minutes to work on it here, so I'm probably not going to solve it now either. But one thing I started thinking about was, well, isn't there a theorem that says if we do this, we've got 2 points, that defines a line. We've got 2 points, that defines a line. If we draw a line like this with a diameter, and both of those lines from the endpoints of that diameter to a point on the circle, then there's a theorem that says this is a 90-degree angle. Turns out, yes, there is. I went about re-establishing that to myself. A good way of proving that one seemed to be to start with a circle, a diameter, a point, and then draw a radius out to it. You then have that. This is a radius, that's a radius, that's a radius. You've got a couple of triangles like that. And from there, it's not too hard to prove up that this angle and that angle have to add up to 90 degrees, which then means that that original angle is 90 degrees. Anyway, that's just sometimes in working on a problem, I vaguely remember something that I probably learned many years ago, and I probably filed this one under not memorizing the fact because the proof seems simple enough that I was confident in my youth that I could reproduce the result anytime I needed it. In retrospect, I wish I'd memorized more of these things and relied less on my ability to prove them under pressure. But, okay, so we've got one right angle. Now, one of the things I thought about in this, excuse me, just to make this extra cheap, I might have to burp occasionally. But I'll try and spare you the noise. One thing I thought about this in this was, how would you do this if you did have a compass? Well, the method that comes to mind using a compass took me, I'll admit, a minute to remember. I'm talking a little faster than normal here for the sake of not making this too boring. With a compass, you could simply measure any length you wanted, set the compass to a length, and then mark points on, you could extend this diameter, and you could mark points on that diameter. Those points are then equidistant from C. Lovely. And then you could construct a perpendicular bisector for the segment I don't really want to draw on here that has been created. That perpendicular bisector would, by basically the standard method, I'm not going to go into that. You can look up how to create the perpendicular bisector of a segment using compass and straight edge. But that perpendicular bisector would go through every point that is equidistant from this point, let's temporarily call it D and E, and the list of all points that are equidistant from D and E includes C, so this line, which would be perpendicular to this line, also includes the point C. It would be the perpendicular from this diameter to C. Great. We can't do much of any of that, but it was worth going down that rabbit hole. One of the reasons, or maybe not, because we were given in the solution of the, or in the statement of the problem, that Presh Talwalkar worked on it, and he stated that he wasn't able to solve it, at least in a reasonable span of time. Almost certainly, giving the man the credit that he richly deserves, he would have thought to try the method that we would use if we did have a compass, so we probably didn't even need to go down that rabbit hole. If that was going to work, he would have found it, and so let's try something else. Something I tried earlier was to say, well, could we just draw sort of a random line or pick a random point? The thing of it here is it's very tempting to just say, well, just draw the perpendicular. But we don't know where the point is on this diameter that we should draw that perpendicular through. We also can't bisect the diameter, so we don't even know where the center of the circle is. One of the ideas that comes to mind to toy with is there some way we could just pick a second random point up here? And knowing that that will also be a right triangle, can we get somewhere with that? Could we somehow use that to at least find like the center of this circle? Doesn't look like it. But this is a lot of what you do in trying to attack a problem that you don't know the answer to, that isn't in the textbook, that is maybe Fermat's last theorem, where no one has a good proof. You start throwing ideas at it. So I made a random point and I drew a couple lines to it because I know I can draw a line through any 2 points because I have a straight edge that was stated in the statement of the problem. Triangles. There are problems in life that can't be solved with triangles. Sorry, Red Dwarf quote. It is at least interesting. Those are both triangles. Maybe I could do something where I just draw a random chord through here that goes through the line segment AC, and then we could apply the chord theorem, which we saw a couple weeks ago on Mind Your Decisions, where we would have AB equals CD. Since we don't actually have measurement marks on our theoretical straight edge, I'm not sure how that's going to help either. There was part of me that wanted to see if we could find a way to construct an actual rectangle here. Despite the poorness of my drawing, this should actually be, assuming that's a diameter and this is a point on the circle, this should actually be a right angle, but there's nothing to guarantee that this or this are right angles, so it's not a rectangle. It's some weird kite or something. If it were a rectangle, and sometimes thinking about how nice things would be if something were true, and then see if you can make that thing be true. If this were an actual rectangle, well, then at least it would be relatively easy to find the center of it, and happy things might happen from there. We might actually from that be able to get the center of the circle. But can we make this into an actual rectangle somehow? Thing of it being, it would be really nice if we had a second diameter that was perpendicular to this one, but with just a straight edge, I don't know how we're going to go about finding the points up here and down here that we would need to draw between in order to get a perpendicular bisector of this diameter, which would then necessarily be another diameter of the circle. So I tried some things. I also considered the possibility of, well, could we create a tangent line? Don't even know how we would do that using just a straight edge, because the usual method for creating a tangent to a circle involves knowing where one of the radii of the circle is and then constructing a perpendicular to it at a certain point. All easy to do if you've got a compass, all mind-bogglingly difficult if all you've got is a straight edge. But it's at least worth thinking about again. If we had a tangent to this point, would it help us to find the perpendicular here? Probably not. What might help would be if we had a line parallel to AB that went through that. Although even there, again, I'm at something of a loss to figure out how just having a straight edge is going to allow us to construct a line that's perpendicular to anything. So having a parallel line, does that really help? One thing I do know is that this line is perpendicular to that line. Is there some way we can somehow rotate that triangle so that it comes down this way instead of going that way? With essentially we want to put well, along with cheap, you get poor labeling. I want to put angle alpha up here somehow. And then we would have our perpendicular, although how we're even going to copy an angle when we don't have a protractor or a compass is a very fine question. And that's it. That's my time limit for this video. So, did I solve it? Nope. So, this presentation has lived up to its title, How Not to Solve It. Lots of little things that are buzzing around my head, ideas that might lead to something at some point, but they haven't yet. Again, the point of all this for me, other than making a fool of myself, is to encourage students that might see one of these problems and say, wow, I could never come up with a solution to something like that. I virtually guarantee I will eventually solve this problem on my own without looking at the solution. But it might take me a while because I've gone up probably some kind of blind alley here and hunting in the wrong place for a solution. There's a problem that I will come back to that was presented on Mind Your Decisions a while ago, where when I finally saw the solution, it took me 5 minutes to get the solution. But I had whiteboard after whiteboard full of calculations going off in the wrong direction and actually discovering some things that were more interesting than the original problem. But for a problem that ended up taking about 5 minutes to fix, I spent probably 5 hours writing down equations that had nothing to do with the final solution. It happens. If you're serious about becoming a mathematician, and even though I'm not an academic, I do know several working mathematicians with PhDs who are professors at universities who publish papers regularly. If you have any illusions about going into that kind of a career, get used to going up blind alleys. I don't care how good you are. If you think you're going to look at the Riemann hypothesis and the solution will just come to you in a dream one night, well, good luck to you. That kind of thing probably happens for some people, although it hasn't yet. Most working mathematicians go out and they try a lot of different things before they hit the right answer. Shall I say that 5 more times, or is that kind of coming across at this point? All right, when I've got an answer solution to this that actually works, I'll let you know. That may or may not be the next video. Oh, this was officially episode -2, by the way. So, I don't have a cool sign-off phrase. Just get out there and do more mathematics. It's kind of like Will Wheaton's Play More Games. Do more math. See ya.